In this lesson, we talk about partial derivatives of functions of several variables. As you know, when we have a function of one variable, like y equals f of x, we know that the derivative is with respect to that variable, like the notation that we have f prime of x or dy over dx. We know that we differentiate with respect to the given variable. Like if it is f of x, it's with respect to x. If the variable is t, it is with respect to t. But in the case of functions of, so this was for one variable. But in the case of several variables, for example, if it is a function of two variables, suppose I have a z equals f of x and y. So we should determine, or we should specify that our derivative is with respect to which of the two independent variables x and y. So that's why in several variables, we use the concept of a partial derivative. By partial derivative, we mean that we differentiate with respect to the specified variable. So as a note, if a function has several variables, we should specify that the derivative is with respect to which variable. First of all, let's see how we define the partial derivatives with respect to the variable x and y. And of course, if it's a function of three variables with respect to x, y, and z. But here in today's lesson, I restrict myself to the functions of two variables. So the function that we have is a function of two variables, x and y. And x and y are independent variables. So before writing the definition, let me let you know what notation we use for showing the partial derivative with respect to x or y. So if the function is denoted by f of x and y, one notation, and that's not the only notation, one notation is if I, on the right lower side of f as an index, I put x. This means the derivative with respect to x, the partial derivative with respect to x. I have not defined it yet, but it's very helpful to know the notation. So f of f index x at xy is the partial derivative with respect to x. And fy of x and y. So in the lower right side of f, I just put a y. That means partial derivative with respect to y. So this is the notation that we use. Now let me define these two. First, let me define the partial derivative with respect to x. So this is the definition. The definition is somehow similar to the definition that you have seen in calculus 1 for the derivative, although that was the definition that you have seen for in calculus 1 was for just one variable, not more than one variable. So the derivative of f with respect to x is the limits as h tends to 0 of f of x plus h comma y minus f of xy divided by h. And in a similar manner, the partial derivative of f with respect to y is going to be the limit as h tends to 0 of f of x comma y plus h minus f of x y divided by h. As you know from calculus 1, the derivative of a function at a point is the rate of change. In fact, the instantaneous rate of change. In the partial derivatives, if I find a partial derivative with respect to x, it tells me that what is the rate of change with respect to the variable x, with respect to the first coordinate, while the partial derivative with respect to y tells me that what is the rate of change with respect to y or the second coordinate. Let's see an example to calculate partial derivatives with respect to x and y, although most of the time, almost all the times, we use formulas that I'll talk about that later to find the derivatives, because if every time you want to use the limit definition of partial derivatives, that will be sometimes quite long. We had a similar situation in calculus 1. When we defined the derivative, first we calculated the derivative using the definition, but later we used formulas and rules to find the derivatives, and that was more efficient and it was time-saving. Although it's important to be aware of the definition and know that what is the concept of the derivative, or in this case, the partial derivative. The advantage of the definition is it always reminds us that we are talking about the instantaneous rate of change. Okay, now using the definition, I want to find using the definition. Find partial derivative with respect to x and partial derivative with respect to y, where the given function is in this way: f of x and y is 5x squared y. So I have a function, f of x and y is 5x squared y. And I want to find the derivative of this function using the definition. Later, I'll let you know that what is the faster way to find the derivative without using the definition. But for now, let me do this example by using the definition. Okay, on the next slide, first I'm going to do the partial derivative of f with respect to x. By definition, it is the limit as h tends to 0 of f of x plus h and y minus f of x and y divided by h. So it equals the limit as h tends to 0. So what was the function? F of two things is 5 times the first thing squared times the second coordinate. That's important because I want to apply these to x plus h and y. So f of x plus h and y is 5 times the first coordinate, in this case x plus h squared times the second coordinate. That was the definition, or that was by the definition of the function. F of x and y was 5x squared y. So f of x plus h and y is 5 times x plus h all squared times y. Then minus f of x and y, we know directly what it is, 5x squared y divided by h. So you find this limit as h tends to 0. As I mentioned, you have seen similar things in Calculus 1, but of course, over there, it was just one variable, not two variables. First of all, I see that a 5 is in common. I can on the top, a 5 is in common. I can factor that 5 out. And so even I can bring it out of the limits. It's a constant. I can do that. X plus h squared is x squared plus 2xh plus, 2xh plus h squared. It's multiplied by y. So each of these terms is multiplied by y. In other words, y is distributed over these three terms. So x squared y, 2xhy, h squared y. Then minus x squared y. No 5 because I have already factored 5 out. And divided by h. So x squared y and minus x squared y, they cancel out. So I will have 5 limit h tends to 0. Between the two terms that you see on the top, h is in common. I can factor that h out. So h times 2xy plus hy divided by h. Now I can simplify h and h. And let's apply the limit to the rest of the expression. So 5 limit as h tends to 0 of 2xy plus hy. As h tends to 0, obviously h times y will tend to 0. So the only thing remaining is 2xy, and then there is a 5 before that. So the final answer is 10xy. So the derivative of f with respect to x is 10xy. Now, at any given point, I just multiply 10 by the first coordinate and the second coordinate. I get the partial derivative with respect to x. In the next slide, I'm going to do the partial derivative with respect to y. I suggest that you pause the video and try to do this on your own using the definition. Try to find the partial derivative with respect to y. So by definition, this is the limit as h tends to 0. F of x comma y plus h this time minus f of x and y and divided by h. This is just by definition the partial derivative with respect to h. So this equals the limit as h tends to 0. What was the definition of the function? Function of f of x and y was 5 times the first coordinate. So f of x and y plus h will be 5 times the first coordinate times, the first coordinate is squared, times the second coordinate, y plus h. Let me repeat. The definition of the function in this case, f of x and y is 5 times the first coordinate squared times the second coordinate. So for that reason, f of x and y plus h is 5 times x squared times y plus h. Minus f of x and y, 5x squared y divided by h. So the limit as h tends to 0. On the top, 5x squared is distributed over the parentheses that contain y and h. So it's going to be 5x squared y plus 5x squared h. Then minus 5x squared y over h. 5x squared y and minus 5x squared y, they cancel out. What is left over is the limit as h tends to 0, 5x squared times h on the top and divided by h at the bottom. H and h cancel out, so the only thing remaining is going to be 5x squared. So the partial derivative with respect to y is 5x squared. Okay, so we did this example using the definition, but what if we want to do it without the definition and obtain the results faster? So I'll redo this without definition. So let f of x and y, it was given 5x squared y. I want to find these two. Without using definitions, or you can say that by using formulas. So partial derivative with respect to x, what does that mean? It means that we are looking at the instantaneous rate of change with respect to x. In other words, I can deal with y as a constant. So in this equation, 5x squared y. If you deal with y as a constant, what happens? It's like 5yx squared. Just x is the variable. Y is, I deal with that is as a constant because I'm differentiating with respect to x. The derivative of x squared is 2x. So the answer is 5y times 2x. So I dealt with y as a constant, and I just differentiated that part which had x. So in other words, I looked at f of x and y as 5y as a constant times x squared. So the derivative is, as we know from calculus 1, when a constant is multiplied by a function, the derivative is the constant times the derivative of the function. So 5y times the derivative of x squared, which is 2x. And obviously, we don't leave it like this. It's just multiplication. 2 times 5 is 10, and xy. That's exactly the result that we got here using the definition. So in differentiating with respect to x, I deal with y as if y is a constant and find the derivative. So this is the way that we'll use to find the derivatives of the partial derivatives. Let me, for this example, also find partial derivative with respect to y. For this partial derivative, which is with respect to y, here I assume x is a constant and y is the variable. So in the original function, 5x squared y, that 5x squared is like a constant times y. So a constant times y, the derivative with respect to y is just that constant part. In this case, just 5x squared. So I dealt with x squared as a constant, and y was the variable. This is exactly the same answer that I got by using the definition. Before seeing more examples, let me mention the other notation that it's used for showing partial derivatives. There are several notations, but this is another helpful one. Like suppose I have a function, z is a function of x and y. So far, the partial derivative with respect to x, I showed it with this. With respect to y, like this. This one can also be shown as by using this notation. This notation is used to show the partial derivatives. Or since z equals f of x and y, I can just say, or I can just write in this way. Same thing, similar thing here. This is partial of f with respect to y. Also, I can show it like this. Excuse me, on the top, I forgot, I repeated z, it was x here, sorry. And at the bottom here, it is respect to y. Okay, now let's see more examples. Again, you may pause after I write down the example and try to do it on your own. So suppose f of x and y is given x to the 5 minus 3xy plus y to the 4. Part 1, I want to find a partial derivative with respect to x. And part 2, I want to find partial derivative with respect to y. So if I want to use formulas for partial derivative with respect to x, I deal with x as if x is the variable, and I deal with y as y is a constant. So the derivative of x to the 5 with x is the variable is 5x to the 4. You know this power rule from Calc 1. The next one, minus the derivative of 3xy with respect to x, and I deal with y as a constant, as if it was 3y times x. And 3y is a constant, x is the variable, so the derivative with respect to x is just 3y. And the derivative of y to the 4, here I should deal with y to the 4 as a constant. So the derivative is 0 with respect to x. So nothing after minus 3y. How about partial of f with respect to y? Now here, it will be opposite. I should deal with x as a constant, with y as the variable. The derivative of x to the 5 with respect to x is 0, so nothing here. Then minus 3xy, I should deal with minus 3x as a constant and y as the variable. The derivative with respect to y is minus 3x. And the derivative of y to the 4 with respect to y is 4y cubed. So let's do another example. Suppose f of x and y is e to the power of xy squared. So the power is xy squared. So it's e to the power of xy squared. In part 1, I want to find the partial derivative with respect to x at any x and y. And in part 2, I want to find the partial derivative with respect to y. Again, I would suggest that you pause the video and try to do this on your own. So for partial derivative of the function with respect to x, I should deal with y squared as a constant. So to find the derivative of e to the power of xy squared, y squared is like a constant, I should use the chain rule, like from calculus 1. The derivative of, so let me explain this in more details, just as a reminder of how we use chain rule. So for part 1, I assume that y squared is like a constant, so I can rewrite the function as e to the power of y squared x. Just y squared is a constant. To find, let me give a name to this. Suppose I call this as t. I want to find the derivative with respect to x. As you might remember, in using the chain rule, we let this be u. Find the derivative of the function t with respect to u times the derivative of t with respect to u. One more time. But first, I find the derivative of u with respect to x and times the derivative of t with respect to u. So here, the derivative of t with respect to x, of course, I use the partial notation, is the derivative of t, this I take as u, is the derivative of t with respect to u times the derivative of u with respect to x. Since there are two variables and I deal with them as one of them as a constant, I deal with y as a constant, I use that partial notation instead of the regular d notation that you have seen in calculus 1. So the derivative of t with respect to u, e to the u, the derivative is e to the u. The derivative of u with respect to x is just y squared. Because I deal with y squared as a constant. Now, what was u? U was y squared x. So the answer is e to the power of y squared x, or xy squared, times y squared. As you know, even in calculus 1, that when you have exponential part and polynomial, or in this case monomial, when they get multiplied, we write the polynomial first. So that's the standard way to show this product. So it's gonna be y squared e to the power of xy squared. The second one, I should deal with y as the variable and x as a constant. Again, that requires using the chain rule, similar to the chain rules that you have seen in calculus 1. So here, again, let me give a name to that. Suppose t is e to the power of y squared or xy squared. Here, I write it as it was, x y squared. On the top, I wrote the xy squared y squared x, because y squared was like a constant for x. That's why, to make it more understandable, instead of xy squared, I wrote it as y squared x. But here x is the constant and y is the variable. So in this situation, I let u be this, so that derivative of t with respect was with respect to y. That was this part. The derivative of u with respect to y, xy squared. X is like a constant. The derivative of y squared is 2y, so that part becomes 2xy. And since 2xy is like a polynomial in two variables, that comes first, and u is xy squared. So the answer is 2xy e to the power of xy squared.